the first device experiment was on diode characteristics. Diode is a two-terminal device. Okay, so let's start with a new schematic, and then let's take one diode. So you have this diode here. Take one. Then you require a voltage source. So you take one voltage source. Okay. And then it is better to put one series resistance, though in simulation it is not essential, but when you do it practically you need to put a series resistance. The purpose is to limit the current. So we can call this resistance as current limiting resistance. And then every circuit should have a ground, so you can put a ground. So then you connect the resistance, the diode, the power supply all in series. So this way our connection is over. Okay. Now we can choose different diodes model which are available here, and these diodes which are starting with 1, 9, 4, 1, 4, 8, etc. These are usually available in the lab. So let us take that one. Now this resistance, the purpose is to limit the current, so let us put some 100 ohm for it, and we will vary this voltage, and when you vary this voltage, the voltage that will come across the diode will also vary, which I will refer to as the diode voltage. And when the voltage across the diode varies, the current flowing through it also varies, which I will refer to as diode current. So diode characteristics is a plot between diode voltage and the diode current. Okay, so we need to plot on the x-axis the voltage coming across the diode, not the voltage applied, but the voltage that is coming across the diode, and on the y-axis the voltage, the current that is passing through the diode. So VI characteristics, V on x-axis, I on vertical axis. To vary that voltage and find out the corresponding currents, we need to do what is called as the DC analysis. So before I do the DC analysis, let me just give a 5 volt here, and then I'm going to run it. So you have to choose the DC sweep. Okay, so for varying the voltage you choose the DC sweep. So the starting voltage you can specify, you can go from negative to positive. Okay, if you want to only see the forward bias voltage, then you can start from 0. So from 0 voltage we will do a linear sweep. This is the source name, so that is V1, and the starting voltage is 0. Stop voltage, let's say 10 volt. The increment decides how many points we are going to evaluate in between 0 and 10. So if you want 1000 points, so 0 to 10 will be divided into 1000 smaller units, so individual variation will be something like 0.01. So in steps of 0.01 we are increasing the voltage applied from the voltage source. Correspondingly, the voltage appearing across the diode will also vary. And then you give the run. You need the diode voltage on x-axis, not the input voltage. So go to the x-axis and change this voltage to the diode voltage. So to do that, it is better to give a label, say D, on this node, which corresponds to the diode voltage. Then you go to x-axis and type voltage at node D. Okay, I think I need to run it again. Let me run it again after changing the label. Voltage on D. So now you can see that the voltage across the diode is changing only up to 0.9 volt or 900 millivolt. Because when you increase the voltage from 0 to 10, the same amount of voltage will not come across the diode, only whatever is left out after dropping across the resistance, which is 100 ohm, that will only come across the diode. Now the interesting parameter that we are after is the diode current. Already we have diode voltage on the x-axis. Now let's put diode current on y-axis. So this is the curve that we get, which is the forward bias characteristics of the silicon diode. So this is a silicon diode. You can see the value of current. Because we have given 100 ohm, the value of current can go near to 90 milliampere. It is better to see these in this manner. Okay, vertical windows. So is it clear so far?
Sir.
Okay. Now you can
Sir.
also, yes.
Sir, can you please explain about that quantity that flow tech you have taken for V1 of D?
I give a label to this node which is connecting the resistance and the diode. I give a name to it. D is the name of the node. So what I did is I changed the x-axis as V of D, so that I will get a diode voltage across the x-axis. On the x-axis I want the diode voltage, y-axis I want the diode current. This is what is called as diode characteristics.
Sir.
Yeah.
Sir, but the source voltage is only 5 volts, sir.
No. Source voltage we have to give some voltage. But actual voltage that is given by the source in the analysis is this command .dc V1 is the name of the voltage source, and it takes values from 0 to 10 in steps of 0.01. So that command is a DC sweep, sweeping the voltage from 0 to 10 volt. As you vary the source voltage from 0 to 10 volt, how much is the voltage varied in across the diode? That is what this x-axis is showing. It is going, say, little more than 0.81 volts. You can see here it is not even going up to 0.9. The reason is that the current becomes so large, around 90 milliampere, Because of the Ohm's law, R1 multiplied by that 90 milliampere will create a more than 9 volt to drop across this resistance. So only the remaining voltage will be dropped across the diode. So it is not linearly rising. The voltage is not linearly rising. Okay, the sweep is linear, but the voltage across the diode is not linear.
Yes, sir.
Okay, so that is the silicon diode forward characteristics. Now let's look at reverse characteristics. So for that we need to edit this. Instead of going from 0 to 10, let's go from say minus 10 to 0. Okay, yeah, in the forward bias we had a current up to 90 milliampere. Now let's see how the current vary when you reverse the polarity of this voltage source. So reversing the polarity of voltage means when I say minus 10, the signs of the voltage source is effectively made opposite. That means minus is on the upper part, plus on the negative part. Alternatively, you can change this direction of the voltage source. You can rotate it and put it. That is how we can do it in the lab. If there is no negative voltage available in the power supply, you can just simply reverse the direction, and then you can make upper part negative. That means negative voltage is connected to P side, which is the triangle of that in the symbol. So that will make P side is connected to negative voltage and the N side is connected to positive voltage. Practically you can do that, but in simulation we have more flexibility. We can just give minus 10 volt. So essentially it is not necessary to reverse the direction. You can just imply that by putting a negative value here. So again, let us run it. I'll put the windows vertically aligned. Again, I don't want this V1. I would like to have V of D. So I will change V1 to V of D. Okay, so now you see the scale is still the same, hardly no change. It is still going from 0 to minus 10, almost the entire range of voltage that we made the voltage source to change. So voltage source is changing from 0 to minus 10. The voltage that is coming across the diode is also changing by the same amount. This is one difference that you see. In the forward bias, when you change it from V1 to V of D, we had only up to 0.9 volt. The scale was going from 0 to 0.9. But now it's not up to minus 0.9, it is up to minus 10. Okay, now let us put the current in the y-axis. So you can see the magnitude of the current is in nanometer. So this is the reverse characteristics, IV characteristics of a silicon diode. You have a current somewhere between 2.4 nanoampere and 2.7 nanoampere. If you want to know the exact value, just go here, take the cursor, and you can measure that. It is exactly minus 2.53 nanoampere. So this is the current that is flowing in the negative direction. And this current is called the reverse saturation current. Later we will derive the expression, but right now you make note of these things, that we have a constant current. Okay, it's essentially a constant current. Though the voltage is changing from minus 1 to minus 10, the current is not changing, it is flat. Flat means no change in the current. So voltage is increased in the negative direction from 0 to -10. No change in the current. Constant current is flowing. That is called reverse saturation current. Its value is around 2.5 nanoampere. And negative value for the current means we have taken the current direction from P side to the N side. Negative means actually this current is flowing upward, because our positive terminal of the battery is in the N side. So current will always go from positive side to negative side. Okay, that is always the case. From the positive terminal of the battery to the negative terminal of the battery, current will flow. But here the positive terminal is downside. Though in the picture it is upside, but we have given minus here, so it is on the bottom side. So from there to the up, the current will go through the diode. So therefore it is negative, because our reference direction is from top to bottom. You can see that in the arrow that you see when you put the cursor on the top of the device. So this is the reverse characteristics of the diode, of the silicon diode. Okay, for this particular number, it is very much dependent on the number. So diodes can be fabricated with the different materials, with the different dimensions, for different wattage. Wattage means for what range of power that you want to use this diode for a particular application. So there are a lot of variations, and all that is available in a data sheet. You can search for data sheet with this number, data sheet of 1N4148. If you search in Google, you will get a PDF file which will describe all the features of this diode. Okay, so that's all about the reverse characteristics of silicon diode. Any question on this? Let us now move on to Zener diode. Okay, so there are various Zener diode here. The smallest cut-in voltage I can see is 6.2, which is available here. Let's see any other. Yeah, 6.2, 6.2, 6.8, etc. So you can choose any of this. Let's say I choose this one, 7.5. So I just replaced this diode with a Zener diode. Then all I need to do is just repeat it. So if I do this, I will get reverse characteristics. So I change it to V of t like before. This one, and then I measure the current which is going from top to bottom. Definitely I will get negative value. Okay, so this is what I will get. Now if you see here, the scale is not really going up to -10 as before. It is just stopping at somewhere 7.5. The reason is that the current suddenly rise up in milliampere, and because of which there is a lot of voltage drop across the diode, and the remaining potential only be coming across this diode. Okay, so this is reverse bias voltage. We are applying 0 to -10, but only up to 0 to -7.5. Whatever applied voltage has come, but after that, because of the current, lot of voltage is dropped across the resistance, and the remaining is coming. Okay, this is negative bias or reverse bias. Okay, so you see there is a voltage at which the current abruptly increase. That voltage is the Zener breakdown voltage, and it is very clear here that it is happening at around -7.5. Okay, if you want to clearly measure it, then you can take a cursor again. You can take cursor and then slightly change this, then you can see the values. Okay, so the value is minus 7.45. that is, so there are two cursor I have taken. One cursor I have kept at minus 7.44, another at minus 7.45. when I vary this voltage by just an amount, diode voltage is varied by 0.01. the change in current is huge. There is around 20 milliampere variation. So you can see here, so this is minus 25 milliampere, this is minus 5 milliampere. From this you can find out the breakdown resistance. What is the resistance offered by the diode after it breaks down, and it will be very, very small. Okay, this change in current, which is 20 milliampere, divided by change in this voltage, which is 0.01. so 20 divided by 0.01, or you can say it is around 10 ohms. It is around 10 ohms. 20 milliampere divided by 0.01 volts. Okay, so it is 0.01 volt is around 10 millivolt. So milli will cancel. So 20 divided by 20 divided by 10. 20 divided by 10. So that is 2 ohms. So it is quite low, and that is the advantage of Zener diode. Once it is breakdown, the voltage is like staying constant, it doesn't change, but current can change very rapidly with a small variation of the voltage, diode voltage. Okay, any doubt on this? Is it clear?
Sure.
Okay, so now you can do the forward bias characteristics. All you need to do is reverse this, that is make it from 0 to 10, and then run again. Okay, so you can see here this also looks like it is a silicon diode, because you see the cut-in voltage is cut-in voltage means you can roughly say at what voltage, forward bias voltage, you have 1 milliampere current. That way you can define cut-in voltage. So this parameter also, after drawing the curve, you can find out and note down in your code. Okay, one is the cut-in voltage, one is the on resistance in forward bias as well as in the reverse bias. So to find the on resistance, what you do, you take two cursors, okay, there are two cursors, and then put one cursor somewhere here and the another cursor put somewhere there. Both should be on the curve. Then what you do is measure delta I and delta Y, delta I and delta V. Okay, so if you look at delta V is here, it is the difference between these two voltage, it is 76 millivolt, and this is delta I, which is 71 milliampere. So it is roughly both are of the order of 70 milliampere. So the on resistance is basically very less. Okay, once it is turned on, the diode resistance is very less. So this is, you take 2 points on the curve and approximate it with a straight line and measure the on resistance. Okay, so this is the average resistance when the diode is turned on, and cut-in voltage is the voltage at which you have the value of current equal to say 1 milliampere. So right now it is 2.1 milliampere. You reduce it and make it 1 milliampere. Okay, roughly. So this is 1 milliampere. You can see here. And this voltage is the cut-in voltage. It is around 0.775. So that is how the silicon diodes are roughly around it. The actual value depends on the construction of the diode, but it is somewhere around 0.7. But for germanium diodes, it will be somewhere around 0.3. So that way you can distinguish between the diodes. So this Zener diode is made up of silicon. The material will decide the cut-in voltage. Any question on this? No question. So the next part I told you to pick a different diode, which is LED. So you can see LED somewhere here. So here is an LED. There are many LEDs here. So let us take one of this. Depending upon which one you pick, the values and the characteristics may vary slightly. LED has this symbol, a diode symbol with two arrows coming out, which shows light is coming out. So let us run it. So there is some change here, especially the cut-in voltage is changed so much. It is increased. So most of the LEDs are made of materials like gallium arsenide, compound semiconductors. They are not made out of silicon or germanium because they are, as we learned, indirect band gap semiconductors. If you remember when we discussed the band structure, there are two kinds of material. One is the material having the minimum of the conduction band aligning with the maximum of the valence band. Such materials are good for emission of light. Okay, gallium arsenide is one such material, and there are many other compound semiconductors which are having this feature, and they don't require any momentum change while emitting light or absorbing light. Okay, so such material are mostly used in making LEDs or even solar cell direct band gap. You can absorb light more efficiently. Okay, if you use silicon, the absorption and the emission of light is inefficient. Okay, then we have to modify a lot of other ways in order to make it or improve its efficiency. That is also a challenge in the solar cell. Okay, but making gallium arsenide devices is also a little bit tedious, and these elements are also not very easily available, but silicon, it is very easily available. So we will always try to work with silicon in electronics industry because the abundant availability of silica or sand. Okay, so now if you look at the cut-in voltage as before, you take a cursor and put it when current is 1 milliampere. Yeah, so this is 1 milliampere. You see the voltage is 1.7. 1.7 volt. Silicon was around 0.7, now it is 1.7, much larger. This cut-in voltage is directly linked to the energy band gap. So if the energy band gap is larger, cut-in voltage is also larger. Gallium arsenide has much larger energy band gap compared to silicon. Silicon has around 1.1 electron volt, whereas gallium arsenide it is something like 1.4, 2, 4, 3, etc. electron volt. Okay, that is one thing you can find. Now if you take 2 cursor, you can also find the slope of this. So let's take 2 cursors and then put one somewhere here and another somewhere here, and then you can see that this curve is also something like a straight line. You have delta V here, so delta V is 2.2 minus 1.8 or 2.3 minus 1.8, that is delta V divided by 68 minus 6.9, so that will give you delta I. So delta V by delta I is the resistance. So you can see that it is much lesser, but not as less as silicon. Okay, here the slope is more less, okay, not very steep. It is so when it is turned on, average resistance offered by the device is slightly larger than silicon. So you can compare the number and write the exact values. So cut-in voltage you can find from forward characteristics. The slope or average resistance after it is turned on can also be found out. So these parameters you write down and compare. Okay, the last thing that you, any questions?
Sir.
Yeah.
Sir, so what was cut-in voltage, sir?
Cut-in voltage, roughly you can take the point at which the current becomes 1 milliampere when it is forward biased. So the value of voltage, diode voltage, when the current, forward current become 1 milliampere, that is a good estimate. Rough estimate, but a good estimate. Another way it is defined is like if you project this straight line approximation, wherever that straight line meet on the x-axis, that you can take it as cut-in voltage. In a way it means at what voltage of forward biasing the device is turned on. That is the question cut-in voltage try to answer. So the answer is that when the current is of the order of 1 milliampere, that is the time we can say the device is turned on. And before that also current is there, but it will be in microamperes, maybe 100 microampere. If you go further before, it may be 10 microampere, etc. But roughly when it is of the order of 1 milliampere, then it will create some good voltage drop across the resistance that we put in series. Okay, so only then it will become visible in the voltage waveforms. You don't see much change if the current is in microampere. That is why earlier when I reverse biased, we did not see any reduction in the diode voltage. It was going from 0 to 10 volt, for example silicon. But once the current will begin to flow in milliamperes, then you will see its effect on the voltages. Voltages start diminishing. So therefore, from what point of time we need to be, what point of time it is going to affect our voltages that we see on a CRO or measure using a multimeter. Multimeter, of course, it will give you any voltage, but to see visually on a CRO that there is a change in the voltage, or here in the x-axis, at least of the order of 1 milliampere current should flow, because our resistance are in say 100 ohm or 1 kilo ohm, etc. If the current is less than 1 milliampere when it is flowing through 1 kilo ohm, the voltage drop across the resistance is less than 1 volt. So it won't be appreciably noticeable. Is that clear?
Yes, sir.
Okay. So the last thing that is left, for the same diode, you do a negative. Okay. Though we use LED only for a forward bias condition, because LEDs do their job in forward biasing. Reverse characteristics is not that important for LED. Okay. Either we give 0 volt or say 5 volt in series with the resistance. Just like you have learned it in digital 7 segment display, I told you each of the segment under that there is an LED. So when you give a 0, you are giving 0 volt if it is a common cathode type. If you are giving 5 volt, that is corresponding to 1, you give a 5 volt in series with the resistance. So that will make it have a voltage greater than 1.6 across the diode, making it forward bias and making the current to flow, and this current is what generates the light. No current, no light. So if you want to see appreciable amount of light coming out, at least some 1 milliampere current should flow. Otherwise you may not notice. If microampere current is flowing, you may not notice any light coming out of these LEDs. So it should be above the cut-in voltage that you apply across the diode in order to see appreciable light coming out. So it is not so important to plot its reverse bias characteristics, but still we can just look at it. There's nothing wrong in it.
Sir.
Yeah.
So do all diodes have a breakdown voltage?
Oh, yes, all diodes have breakdown voltage, but the silicon diode in 0 to 10 volt we did not have any breakdown. But if you go further, smaller and negative voltage, like say 100 volt or maybe 200 volt, definitely it will break down. Somewhere in between it will break down, and it varies with the diodes and its construction. So if you plot it, though as I said, it is not very useful information that we have here, but still if you want to plot it, you can see it has a very negligible current and it is not constant also, so you can just note it down. So it's a very negligible current. The smallest of all the current we have seen so far is picoampere, which means 10 raised to minus 12. It may vary with the number, but as I said, for LEDs we generally don't care about the reverse characteristics. So if for this particular diode, if you don't plot it also, it's okay for me. And the scale that you plot, you should if you plot it in milliampere, you will see 0. If you put the scale here in milliampere instead of picoampere, from bottom say 1 milliampere, and these ticks are in 0.0 or 0.1 milliampere. You see that nowhere to be seen. So you can say that it is 0. This way also it is okay. So it depends whether you get a straight line or you get 0, depends on the scale that you look at. So normally we are interested in currents which are of the order of milliampere, then you can say that it is 0. But silicon diode, you plot that in nanoampere, but all other you can put it in milliampere. Because silicon diode, it is constant and it has a name. We will look at it. It is called reverse saturation current. The value also you need to note it down. But here it is not constant actually, and it is very negligible also. Even if I plot this in nanoampere, you will see it is so negligible. So So if I put nanoampere here, and here I will put 0.1 nanoampere. See, then also you see that it is negligible. In nanoampere also you don't see appreciable current. Very, very negligible. Okay, so that is the experiment number 6. So if there is any more doubt, you ask. Otherwise, you should be able to do it all.
Sir.
Yes.
Sir, I have one doubt regarding abrupt change in that voltage. Current, sir.
Abrupt
In
change.
breakdown voltage, sir.
In the case
Sir.
of Zener diode.
Yes. In case of LED, sir.
In case of LED, we don't have any abrupt change.
So the current is constantly increasing.
Where? In
after voltage.
Reverse or forward?
So for the forward.
Forward, we don't say it is breakdown. That is not breakdown. That is device turning on. Okay, it is wrong to say breakdown. Breakdown is entirely a different mechanism taking place. That happens in the case of Zener diode that we saw in the reverse bias condition. That is a breaking down. But when you forward bias a diode, any diode, it will turn on at some point of time, which we call as the cut-in voltage. Okay, what is your question regarding that?
Sir, so that voltage gets dropped 100 ohms, sir. So
Okay.
means like so around when we have taken 100 ohm resistance.
Yes, yes.
So then all the voltage get dropped across 100 ohm resistance. Then very little amount of voltage is flowing through the diode.
Correct.
But sir, still is it's increasing current.
Current is increasing. So yeah. So you see that here, if you look at the voltage drop across the diode, the LED is 1.6 volt, right here. Then it increased to 1.8, 2 volt, etc. Okay, what we have given is 10 volt. Maximum voltage that we are giving is 10 volt, but here it is going only up to 2.3 volt as per this graph. So the rest of the voltage is dropping across the resistance because current is increasing. Current is around 70 milliampere here. So when that much current is flowing through this resistance, it will create around 7.5 volt drop. Okay?
Yes, sir.
Only the rest can come to the diode.
So that means that's enough for the LED to turn on.
Yes.
Okay.
Or in other words, only when the LED is turned on, this current can flow and the drop can come across the resistance. Because they are in series, no? Whatever current flows through the resistor is the same as the current that is flowing through the diode. So only when the diode is turned on, then only voltage can drop across the resistance.
Okay. Yes, sir.
Yeah. Any other questions? Okay, so shall I go to the next experiment?
Yes, sir.
Okay, so we will now go to experiment. So this is diode CAD. Okay, so next we are going to take a device which is transistor. That is the most central device in electronics. You take any chip, it's full of transistors, and transistors are basically of two types. So today we are going to look at what is called as the BJT. BJT. So that way it is not available. Either you have to type NPN or PNP. So let's take NPN transistor. We are yet to study this, but you can look at the characteristics, okay? Even though you don't know exactly what is going on inside, a device can be characterized by setting different voltages across its terminal and trying to see what happens to the current, how the voltage and the current are related. That's all what we are doing now. Okay, we are not interested so much in what is happening inside. That we will study in the theory, but how the current and voltage are related in a BJT. BJT means bipolar junction transistor. So there are three terminals here. So their names are emitter, the one with the arrow. That is this. This is emitter. Then you have base. That is the one which is on one side of the line, vertical line. And then you have the collector. Okay, E, B, C. These are normally the letters used, capital letters used to signify emitter, base and collector. There are three terminals. Since there are three terminals, we need at least two voltage source. And secondly, we need to take one of the terminal as common terminal. So today, what I'm going to do is take the emitter as the common terminal. Let's take emitter as the common terminal. Okay, I need a ground, then I need a voltage source. So this is my voltage source 1, another voltage source, okay, so two voltage sources. Then now this is an NPN transistor. That means base is P, emitter is N, collector is N. So you can think about a P material sandwiched between two N material. And what we are going to do is, we are going to bias this junctions. Just like we have biased diodes, either forward bias or reverse bias, I can also forward bias or reverse bias these junctions. Let me shift the ground a little more down. Okay, so I am going to bias the one of the junction like this. So now, depending upon what voltage I give to V1, it will decide whether I am forward biasing or reverse biasing. For the time being, I am avoiding any resistor, but if you are doing this in the lab, you have to put a resistor, otherwise you will end up destroying the device. But in simulation, it is okay. Okay. I connected two voltage source like this. At least one resistance you have to put if you are doing this practically in the lab. Okay, maybe I should put the resistor, otherwise I will encourage a bad habit, because in simulation you can be free like this. So I put a resistance only here. The reason is that I'm going to forward bias this junction here, the junction between base and emitter. because base is made up of P material and emitter is made up of N material. So I am going to forward bias it. So in order to forward bias, I have to give a positive voltage here. So let me give a positive voltage, say 2 volt. Since I have put a resistance, I can give 2 volt. But if I am not putting any resistor, I should give a 0.7 or 0.75 like that. Otherwise, we will end up destroying the device. Forward bias voltage across a diode can be maximum 0.8 volt or 0.85. It is a silicon. Okay, I am assuming a silicon. If you want a particular silicon transistor, you can take that also. BC547 is something that we use in the lab. Okay, so that is here. So let's put that. And the purpose of this resistance is just to limit the current, so that the forward bias diode doesn't get a very large voltage, forward bias voltage. So you can put something like say 500 ohms. Just to protect the device. But in simulation, of course, you can be without it, but it is better not to learn and practice like that. Always put a resistor whenever you bias a junction, forward bias. Otherwise, you can generate immense current and it will burn away the device. Okay. So, and now let me give a value for this voltage. This voltage I am going to give initially 0 volt. 0 volt means I am not giving any potential. I am just connecting this just like a wire. This is just equivalent as connecting emitter and base. But let's see what happens. Now it's a good idea to give some names. So base, I will use capital B, but the program doesn't distinguish capital or small letter. That is base. Then one I will give for collector also. Base and collector, I gave the label for the nodes B and C. Now all values are given. Now we need to perform a analysis again. If you give a fixed voltage like this, then we would like to know the operating point. So the command is .op. You just give and it will give you the list of voltages and currents for this particular device. You can see here I have given the label B and C, so you can identify which voltage. The voltage on the base is 0.71. Okay, it's 0.71. Why? Because it's a forward bias diode. You can't increase the voltage so much, and to protect that forward bias junction, we are putting a series resistance 500 ohm. And in proportion to this voltage, like earlier, a current IB will flow. And what is the current IB that is flowing? It is of the order of 2.5 milliampere. 2.5 milliampere is the current that is flowing. Okay, and then what about collector terminal? What is the current flowing? As I told you, we are giving a 0 voltage for the collector terminal, so VFC is 0. The current through the collector, that is IC, is negative. Okay, and it is minus 2.7 milliampere. Okay, I am converting whatever is given is in amperes, but I am converting that to milliampere. So we are getting a getting the values of voltages and current for the given applied sources for the given circuit. The drop across the resistance is this current, that is 2.5 milliampere, multiply with 500. Okay, so this is one way you can find out the operating point. That means where is the device operating, what are its terminal voltages, what are its terminal current. Any questions?
Sir,
Yeah.
sir, why across that current across collector is negative, sir?
Yeah, so when you run it, so let me do a different analysis. I'm coming to your question. So here, instead of this, if I say DC sweep, which is what we are going to do next. When you put the DC sweep, I can change the input voltage, this voltage, from, so V1 is the voltage source I would like to sweep linearly, starting from 0. I'll go to say 5 volt. But that doesn't mean the forward bias voltage is going to go to 5 volt. There is going to be a drop across the resistance, and the remaining will only be coming across the forward bias junction. Okay, and again let's say this is 0.01. And then let us run it. Now, coming to your question. Okay, so when you find the current here, I would like to plot this current. So you can see that it is negative. Why is that? It is because the direction of the current that it is plotting is coming out of the terminals. Okay, the direction of the current, okay, let me see, direction of the current that is plotted is coming out of the terminal. So each of these, when you bring the cursor to each of the terminal of the transistor, there is a symbol change, you can see. This is the cursor cross line, but when you bring it into the terminal, you have something like a black thing. So when you click at that time, you will see you will see the plot of the current. So all the time for the transistor, one thing is to be for sure, that the Kirchhoff current law should be valid. That means if some current is coming in, it has to go out. Okay, so if these currents are current coming into the terminal, so all this current, when you add up, they should go to 0. So you take any point here, you take a cursor, you take any point in this, so you add these three current, they will cancel each other to 0. That's because all the current which are coming into the terminal, they add up to 0. Okay, so this way we can find out whether this simple, it is not very clear whether it is coming into the terminal or going out of the terminal. The arrow direction is it's not very clear. So but one thing is sure, current goes from positive to negative in the base, and since that is positive, you can say that the base current is flowing into the device. So that is for sure, because we have given a positive voltage and current should go into the base terminal. So the red one is that current, base current, and it is positive, which means that the terminal current is shown as if it is going into the terminal. The current is going into the terminal, not out of the terminal. Okay, so the answer to your question is, so when I give this, it is showing current into the terminal, and the current into the terminal is negative, means current is actually flowing out. Okay, if we are plotting current into the terminal and it is coming negative, means the actual direction of current is not into the terminal, it is out of the terminal. That is the answer. Is that clear?
Yes, sir.
Yeah. So the collector current is coming out of the terminal. Now I am not telling why it is happening. Okay, this is how it is happening when I give a 0 volt. Now we are going to change this voltage and we are going to increase this voltage in a moment. Okay, and what about this emitter current? If the current which is plotted is into the terminal, if it is into the terminal, then for some time it is going into the terminal, but then again it becomes negative, and again it becomes negative and come out of the terminal. Whenever it is negative, it is coming out of the terminal. Whenever it is positive, it is going into the terminal, because the ngSpice is plotting terminal currents which are into the device. Okay, so these are just warming up. We are yet to look at the final characteristics. So I'm coming into the final characteristics in a moment. So here what you can do is that when I give V2 as 0 volt, what you can do is plot the input characteristics. What is input characteristic? You have to take the input voltage, that is V of B. This is just a diode, nothing more than that, which we have already seen. A PN junction, we are applying a voltage and plotting the current. So current is flowing into the terminal. Yeah, now it is very clear that the arrow is showing into. Earlier that was not happening. Okay. Yes. So this is the diode characteristics. For better clarity, I will put it like this. just a diode characteristics, a silicon diode characteristics. Okay, so you are applying these voltages between base and emitter. So this VB which I wrote here is nothing but VBE. Input voltage is VBE. Input voltage is VBE. Then input current, input voltage versus input current. Input current is IB. Should be suffix actually, but here I can't write suffix, so just writing IB. So input voltage is VBA and input current is IB. So IB versus VBE is what you are seeing. This is called as the input chara. Now you are seeing an input chara for V2 is equal to 0. V2 is what? Collector to emitter voltage. V2 is 0. I kept V2 0, which is collector to emitter voltage 0. I vary the base to emitter voltage and note down the base current. So this is called as the input characteristics of the BJT, NPN transistor. Okay. Output voltage is kept constant 0 in this case, and then vary the input voltage and note down the corresponding variation of the input current. This is called input characteristics in common emitter configuration. See, emitter is taken as common to both voltage source. So you have to take one terminal common, and that is what is grounded also. Okay, so every voltage is measured with respect to the common terminal, the base voltage as well as the collector voltage. It is measured with respect to the common terminal, which is emitter. So common emitter configuration, this is the input characteristics for a particular output voltage, which is V2 equal to 0. Now what I am going to do is, I don't want to keep the output voltage just at one value, but I would like to see the input characteristics for different values of V2. So I need to edit this. I can specify the second source V2. I will vary this linearly, and then start value again I say 0, stop value I will say 10, but I will go in steps of 5 volt. That means 3 curves I will get. The first curve for 0 volt, input characteristics for output voltage equal to 0 volt. Then the second input characteristics I will get for output voltage equal to 5 volt, because increment is 5. Then again I step up the output voltage by 5 volt and it will be 10 volt. So 0, 5, 10. The question is, will the input characteristics vary, or will it be same curve that is going to be repeated? Let's see. So let me run. Now you can see 3 curves. First curve is the, I hope this is corresponding to green, 0 volt, and then next one, okay, let us make sure of that. If it is So yeah, the green is the first curve, and then the blue, then the red. Okay, now I'm doing all the three curve. Okay, so green, then blue, then red. So this is the way in which color changes. So first case correspond to 0 volt, output V2 voltage, that is VCE is the output voltage. Output voltage VCE. Okay, so you keep the output voltage constant either at 0 or at 5 or at 10. Okay, and do the input characteristics, that is gradually vary the input voltage and see the variation of the input current, and you are getting 3 curves correspondingly. Any questions?
Sir.
Yeah.
So what is the notation that you use, sir? VBE for input voltage.
VBE, voltage between base terminal and emitter terminal, that is VBE. IB is the current into the base terminal. And VCE is the voltage between collector terminal and emitter terminal. You can also call it as collector voltage minus emitter voltage. That way also you can say, because it's a potential difference. Potential at the collector terminal minus potential at the emitter terminal is VCE. The first curve corresponds to a case where it is equal to 0. The blue corresponds to the case where VCE equal to 5 volt, and the red corresponds to VCE equal to 10 volt. Any other question? Any other question? So this is called the input characteristics of an NPN transistor in common emitter configuration. You are able to understand everything which I am saying. There is common emitter configuration, there is input characteristics, which is a plot of input current versus input voltage, keeping the output voltage constant. This is what is called as input characteristics, and it is more or less a diode characteristics.
Sir.
Yeah.
But can you please explain about the working of transistors? And sir, what is it actually?
Yeah, we will come into the working of transistor, what is going on inside, all of that later in the class we will come in. Right now, without discussing all the basics, it will be very difficult.
Yes, sir.
So,
sir, what does it does means?
Right now you see it is just like the diode characteristic which I shown you earlier. The diode characteristics when it is forward biased. So we have a PN junction between base and collector. We are forward biasing just like this. This circuit is exactly the previous circuit. There is no difference. The only difference is that we have an additional path for current to flow, which is the collector terminal through this voltage source. But in input characteristic, we are not looking at that part. We are just checking this current and this voltage. The PN junction voltage is what we are plotting here, and the diode current is what we are plotting in this, the junction current. So just if you understand the diode, then it is just the same, but there is some dependence on what voltage you give here. That right now I cannot explain. I'll explain it a little later. There is some dependence, and what is the dependence? It is actually bending the curve down. As you increase this voltage, you see that the curve moves initially so much, and then it moves. Let's put more voltages at the output. Instead of step of say 5, let's put step of 1. Then you will see more fine detail. Oh, but what you see is that only one curve is very different from the other curves, and that is the case of voltage 0. But all the so there are 11 curves, 10 of them are like very much close to each other, but one curve, which is 0 volt, that is far apart. So this variation is happening between 0 and 1. So let us focus that 0 to 1. Let's say increment with 0.2. Okay, so now you can see more clearly the variation that is happening, because after 1 volt there is hardly any variation. You can't see the variation, but here now you can see what is happening. Okay, so this is for 0 volt, then it is for 0.2 volt, 0.4 volt, 0.6 volt, 0.8 volt and 1 volt. 0.8 and 1 are almost on the top of each other, so you can't distinguish it, but there is variation as you increase. So there is a lot of sensitivity with respect to small voltages, but with high voltages it's all same. Any voltage above 1 volt, no much difference. So these are the conclusion you have to draw out from this curve. You don't know what is happening inside, but you can see the characteristics and you can make your own conclusions. First conclusion, they all look like a diode characteristics. There is a cut-in voltage somewhere around 0.7, and the only difference it makes with respect to the output voltage is that the cut-in voltage is increased. Cut-in voltage is increased as you give a positive voltage. Even if it is a minor 0.2 voltage, cut-in voltage is increased, and then its slope gradually reduces as you increase this voltage. So draw out these conclusions from this curve. That is the job I am giving you. That doesn't require what is happening inside. Okay, but this is how you study. This is the way we study atoms. You look at the spectrum and then we talk about what is inside. So here we are looking at the IV characteristics and we are trying to understand how this device works, what way the device works. When we do not have access to the inside world, we can look at the characteristics from external point of view. Any questions regarding input characteristics? If you are asked what is input characteristics, you should know. Now, input characteristics is a plot of input voltage versus input current, keeping the output voltage constant. And you can do that for common emitter configuration, common base configuration, common collector configuration. So what we are right now doing is common emitter configuration. I have taken emitter common to the input and output side. Input side is base, output side is collector. This is how it varies. Is it clear?
Yes,
Yeah. Okay, now let's go to output characteristics. Now what is the output current? Output characteristics, just like I said about input characteristics. If I say what is output characteristics, output, it is a plot of output current versus output voltage for a fixed input for a fixed input voltage or input current. Okay, you keep the parameter for the input constant, vary output voltage and see what is the variation of output current. So what is the output current here? In common emitter configuration, the output current is IC, that is collector current. So we are going to now see the variation of these two, this versus this, by keeping this constant. So to keep this constant, what I can do is like I will remove this resistance and keep a fixed voltage here. I'll cut it. I'll cut this. I'll remove this and this I will give as say 0.7 so that it will not change. That's the idea. Okay, so V1 is kept at 0.7 and then the DC analysis I will change. This will be V1 and I want to start from say 0.7 to say 0.8 in steps of 0.02. Okay, I will keep it as 0.7, 0.8, 0.02, etc. Sorry, in steps of 0.02. So that means 0.7, 0.02, 0.72, 0.74, 0.76, 0.78 and 0.8. So there will be that many characteristics. So V1 is the second source. Now first source is V2 for output characteristics. First source is V2, which is our output, and this I will vary from say 0 to say 10 volt and vary, and in smaller steps 0.01. Okay, what is output characteristic? It is a plot of output current versus output voltage. So let me make this into the output voltage, which is V2. Okay, so V2 has already come here, so that is correct. V2 is the VCE. Now what I want is the terminal current, the current that is going into the collector terminal. Okay, and you can see the characteristics. Apart leaving the very small voltage, that is 0 volt, near to that, every current is positive. That means they are all going into the collector terminal in the direction of V2, from positive to negative. but there is an exception. When V2 is 0, the current is negative. It's going to some minus 9 milliampere. That's what we earlier also saw. So the green curve corresponds to 0.7 volt. V1 equal to 0.7. That is VBE is kept at 0.7. It is not varying. And then next one is 0.72, then 0.74, 0.76, 0.78, and the last one is 0.8 volt. Typically a forward bias junction will have to be between 0.7 and 0.8 for silicon diode. Questions? Ask questions. You understand what is meant by output characteristics? Did you understand?
Yes, sir.
Okay. So again I repeat, output characteristics means plot of output current. In this case it is collector current versus collector voltage. Keeping the input voltage constant. Earlier we kept output voltage constant, and then we saw input characteristics. Now we are keeping input voltage constant and showing the variation of output current versus output. So what can you learn from these two? In the case of output characteristics, you can see that the curves are flat. The curves are more or less flat, which means that when you vary V2 from 0 to 10 volt, the current is staying constant. Very important observation. This should surprise. And that is this property is at the heart of transistor becoming useful as an amplifier. Questions? Ask questions.
Sir, can you please repeat, sir, what you said?
If you look at this curve, you can see that the output current doesn't vary much with the output voltage. Output voltage is changing from 0 to 10 volt, but the current is almost remaining constant. There is a slight variation, but that is not appreciable. Do you see that?
Yes, sir.
Yeah. But for input characteristics, the dependence was very strong. But for output characteristics, the dependence is very negligible. Which means, if you find the resistance, the average resistance that I told you about, you can do that for this curve as well as for that curve. You pick up any particular color, take 2 points, take the cursor and take 2 points. Just by clicking on this, you can take 2 points. Take this cursor, it's 1 and 2, and then put one here, somewhere here, and the second one somewhere there. Then you can see the horizontal variation. These are in volts. The change of voltage is around 5 volt. Voltage is changing by 5 volt, but current is changing by 6.6 milliampere. Very negligible change for a large change of voltage. So if you take the ratio delta V by delta IC, that is 5 divided by 0.6 0.6 milliampere. It's going to be large. It's milliampere. Okay, so 5 divided by 0.6. Let's do it. 5 divided by 0.6 milliampere. So 5 divided by 0.6, that is 8.3. 8.3 kilo ohms. 8.3 kilo ohms. That is the resistance that you get out of this curve. It's an IV characteristics. Output characteristics is an IV characteristics. We are plotting change in the current with respect to the change in voltage. But from the curve you can take 2 points of any color. Okay, you can take the magenta or cyan or red or whatever color, and you can calculate the delta V and delta I from these values. So here it is delta V, and this is delta I. So delta V by delta I, if you do, you get 8.3 kilo ohms as the output resistance, average output resistance. Is that clear?
Yes, sir.
Okay. Similar thing you can do for the input characteristics, which is looking like the diode. As I told earlier, you take any color, pick 2 points, and then find delta V by delta I. You will see that it is much smaller. Maybe it is something like 10 or 20 ohms. So input resistance average value comes around 20 ohms, whereas the output resistance comes around 10 kilo ohms. So input resistance is 10 or 20 ohms. 10 ohms, let's take 10 ohms. The output resistance is something like 10 kilo ohms, which is 1000 times larger. So there is a large difference between the input resistance, average input resistance, and average output resistance.
Yes, sir.
And therefore the name transistor is often called as, it came out of this difference, that is transfer of resistance. That's how the name transistor comes. Transfer of resistance. In the input side you have very small resistance, in the output side you have very large resistance. Okay, so there's a transfer of resistance. Okay, there's a difference, large difference. I mean, it depends on the configuration also, how this change exactly depends. Okay, if you take another configuration, you can do the opposite also. Like if you take common collector configuration, then there, if you take your input resistance and the output resistance, that will be entirely different thing. Input resistance is going to be very large and output resistance is going to be very small. That's a different configuration, but nevertheless there is difference. That's what I am stressing. That's difference. One is maybe smaller and the other is very larger, or one is maybe larger and the other is smaller. And different scenarios are useful for different application. You will see that in a later course, not in this course. You have application of different configuration for different application. But the point I am making is that there is large difference between these resistance at the input and resistance at the output. So transistor is a device which can take a signal from one resistance region to another resistance region. It can transfer that signal from one resistance region to another resistance region. So therefore the name transistor. So this resistance aspect of these characteristics are important. So you have to do this I have shown it for common emitter configuration. Later I will show you also for the next class for other configuration. There also you can do the same analysis, okay, plotting the input characteristics and plotting the output characteristics. Now today I would like to close with one more characteristics. And the characteristics I want to close with is I will change the x-axis to V1. I change the x-axis to V1, or let me say V of B. And I have to change this analysis also. Now the first source I want again to bring it as V1, linear from 0, not from 0, from 0.7 to point, or let us put it from 0 to 0.8. Okay, 0 to 0.8. I am dealing in smaller, finer steps, in steps of 0.01. Second source I will keep it V2, and V2 I will vary from start value, say 1 to 4. Okay. So 1 to 5, let's say, in steps of 2. Okay. So this is very different. This is neither input characteristics nor output characteristics. Okay, that I am going to plot. So let me do it again. I am going to run it, and I am going to take this terminal current and plot it as a function of V1. Terminal current is what? Terminal current is collector current, this terminal current. So I am plotting the output current versus input voltage. Output current versus input voltage. And this is what I get. I did it for various values of output voltage, that is V2 equal to 1 volt, then 3 volt and 5 volt. 3 curves are here, but it may not be very visible here. They are all almost at the top of each other. You can see here. They are almost very close. Okay. This characteristics, which is the third characteristics of the transistor, is called transfer characteristics. Why is it called transfer characteristics? Because what is plotted on the y-axis is something related with output. What is plotted on the x-axis is something related with the input. Okay. So therefore the name transfer characteristics. IC versus VBE, keeping output voltage constant. IC versus input voltage, that is VBE, keeping output voltage, which is VCE, constant. So this is called the transfer characteristics. Mostly in the books this may not be plotted when you study devices, but it is a very useful characteristics later in the following courses. Next semester you will study a course on analog electronics. There this characteristics can explain a lot of things. So this is the third thing I want to ask you to plot. And there is hardly much variation when you change. That I told you, because I am starting from 1. So when you start the output voltage from 1, then change it by 2 volt, and again change it by 2 volt, you get 3 curves which are almost close to each other. But instead of starting it from 1, if I started it from 0, then one of the curve, as we saw earlier, would be different. It's going in the negative direction, which means the current is not really going into the device, it is coming out of the device. Okay, which I showed in the output characteristics also. There is some minus 9 milliampere. Now you can see it is close to minus 9 milliampere. That's at the that's at the edge. Okay, usually we don't operate the device there. We make sure that this voltage is at least above 0.2 volt or 0.3 volt. So that is why I avoided that point initially. So you can put 0.3 here, starting value, and then the negative current can be avoided. All are positive. 0.3, then 2.3 and 4.3. 3 curves, they are all one on the top of the other, looking like diode characteristics again. But this is not the input characteristics. And to see that, you have to look at the vertical axis. You will see that it is much larger current compared to the current that you saw for input characteristics. So notice that you have, say, for transfer characteristics, you are getting something like 70 milliampere. Now if you repeat what we did for input characteristics, which I can do now, all I need to do is basically measure this current instead of the collector current. So let me just close it, run it again, and measure IB instead of IC. What I showed earlier is IC, which went up to 75 milliampere, but now let me show you that if I plot this IB, it is not going into 75 milliampere. Look at the figures. It is 400 microampere. 400 microampere, much lesser. That is 0.4 milliampere. So you see 75 divided by 0.4, which is around 180. So collector current is 180 times larger than the base current. So don't confuse, though both look similar. They have a similar look, but they are not the same. Input characteristics and transfer characteristics, they look same, but they are not the same. They are different by a factor of around 180. And that 180 is usually called as beta. That's called beta. So you take, in order to find beta, all what you need to do is you will fix the x-axis, say 720, measure this current from input characteristics, Then you do the output characteristics by clicking sorry, that is not voltage, sorry, that is not current. So measure this current. So you can see that for the same 0.72 volt, you have around 16 milliampere here. 16 milliampere, that's 720 millivolt. You have around 16 milliampere. Take the cursor to get the accurate value. But if I measure for the same voltage, what is the IB? So you note it down, this is around 16 milliampere at 0.72 volt. So now I am deleting this and running again. Now if you measure for IB at 0.72, which is around 60 microampere at the same. So then the ratio 60 divided by 0.06. Okay, so that is the beta. That is accurately, you can that way you can measure the beta value at that particular voltage, that is VBE equal to 0.72. Okay, so that's all I want to say, but if you have any more question you can ask. You should be able to know from this experiment how to do input characteristics, how to do output characteristics, what is input characteristics, what is output characteristics, what are the things that you can find out from these characteristics, and also transfer characteristics. Any questions?
Sir.
Yeah.
So what should be its title, sir? Experiment.
This is the DC characteristics of a BJT in common emitter configuration. Or you can say simply write NPN. This is NPN. We did with NPN. We can do the same with PNP also. So common emitter characteristics of an NPN transistor. That will be okay. Okay, common emitter. Sorry, what did I say? Transistor this is NPN transistor, common emitter configuration. Okay, so characteristics of an NPN transistor in common emitter configuration. Characteristics of NPN transistor in common emitter configuration. Okay, so that will specify this particular set of curves. And there are three characteristics I told you. One is input characteristics, second is output characteristics. So you need to define what is the input variable, voltage and current, output variable, voltage and current, and then also transfer characteristics. So what is plot with respect to what? What is kept constant? Okay, and what can you find out from the curve? And the thing that we found out from the input characteristics is input resistance. From the output characteristics we found output resistance. From the transfer characteristics we found beta. By comparing the input and the transfer we found beta. So these are the things for this experiment number 7. Any questions?
Sir, for the previous experiment?
That is diode characteristics.
To study that characteristics.
Yeah, diode characteristics of silicon diode, Zener diode, and light emitting diode.
Yes, sir.
Yeah. And then within that you have forward and reverse. So that you don't need to put it in the title, but when you write the details, you can put that. So from this, what are the conclusions that you get? You have seen that input current is very sensitive to input voltage, whereas output current is very less dependent on output voltage. Output current is more or less independent of output voltage, and the transfer characteristic shows output current is much dependent on the input voltage. That's what this curve is saying. Okay, this is input characteristics, but if you plot this one, you can see output current depends on input voltage, not on output voltage. It is depending on the input voltage. The difference with the output voltage is these three curves, but they are very close to each other. You can't even see this one. This is the only dependence on output voltage. Output current on output voltage dependence is this. They are almost very close. But this variation is with respect to input voltage. So that is very key understanding that you should have from this experiment. You can control output current using input voltage. Okay.